Hey, John here. Let's talk about the Lattice ICE40HX series of FPGAs. As always, thank you very much to my Patreons. You really do help out. This is a lot of work, and you help defray at least the cost of the boards that I end up rifling through when we do these videos. Thank you very much. So to find the copy of the same manuals I'm talking about, you can go to this webpage here at GitHub. It's my breakout board that I'm going to be dabbling around with eventually here. And I'll put a link in the description below this video if you can't read it on the screen here. It has some links down here to the ICE40 family page. This is the datasheet we're going to talk about today, this link right here. Click that and you'll get the latest version of the ICE40HX family datasheet. Now, as you can see, this thing has, about 40, 50 pages or so. I'm not going to go over the whole thing, but let's look at this from the really top-level view here. It is the overall architecture section here. It's only 10 pages there. And then they talk about all the electrical things, what voltages, when the chip turns on and off, that sort of thing. And if you're going to flip through these, be very careful whether you're reading the sections on LP or the HX, okay? Chips are very similar. The LP ones are low power, and the HX are the higher performance ones. I use the HX. So everything that I say will be related to the HX devices, okay? So let's look at the architecture section in here. That's the whole point today. Let's go down here and find it. Now, this datasheet has some pictures and stuff in here that I think are pretty useful. If you read the entire datasheet, and I strongly suggest you do, because there's a lot of terminology involved in this thing. I'll point it out as we go. A lot of this introduction is going to be about the terminology, and the Lattice terminology in particular that relates to this FPGA chip, so that later on when we talk about things, you know what the heck I'm referring to, or at least you know where you can go look up what all these words mean if you forgot, okay? Bird's eye view of the features, right? It says we have 5 different devices. That includes the LP and the HX chips that have between 384 and 7680 LUT4s and between 10 and 206 I/O ports, all right? Well, that's quite a range, okay? So we'll see a little more about that when we look at the pinouts and the diagrams in a minute. We talk about low power, 21 microamps of standby power and so on. These things do not heat up at all. Even when I run them under full load and get everything going at high clock speeds and they're all chattering away, I don't even detect the slightest temperature difference. So you don't have to worry about heat sinking or anything like that. Real easy to power these particular chips. They're just not that big. They're just not that power consuming. They include distributed memory. We'll talk about this block RAM. I'll make a video on just that. But the short of it is that there are blocks of memory inside the FPGA, and you can gang them all together if you want. There's 128K bits in total up to this much, but the chip we're using has that. And we can use them all in separate blocks. We can make things out of them like FIFOs for UARTs and SPI controllers. We can actually use them as memory if you want to download an entire, simple CPU design into the FPGA. You can use this as its memory and so on. These are pretty handy. I've never seen an FPGA that does not have block memory inside of it, okay? So this is a pretty generic feature that many FPGAs have. Pre-engineered source synchronous I/O. This refers to the fact that if you want to use a DDR-style interface, there are some assisted mechanisms inside the FPGA. This is a very common thing to see in modern FPGAs as well. DDR support. I'm not using it, but it's nice to know it's there if we run into it. Now, they talk about high current LED drivers. If you're going to hook up LEDs to the pins of your FPGA and you need a lot of current to light those babies up, you need a high current driver. You can either use an external chip or you can use some reserved pins on the FPGA that have high current drive. Turns out the HX chips do not have this feature. Oddly enough, the LP ones do, but maybe that's why they need them. The HX chips supply, if you scroll down to the DC voltage section of the manual, it says it'll supply 8 milliamps, either positive or negative. And if my LEDs that I'm going to use in my design only need like 2, so I'm not that concerned about this. All right, so as we move forward, I'm not going to concern myself with this at all. A high-performance flexible I/O buffer. This will be something that we need to talk about. I'll probably put a whole video together on just this as well, because there are custom configuration settings that you can use to turn on and off pull-up resistors. And as you can see over here, they got different types of voltages and support for things like LVDS if you want to use that. I'm not going to mess around with this, but I will be running mine in LV CMOS 3.3 volts. The rest of these are, again, nice to know that you can have them available if you want them in another design. Schmidt triggered inputs. This is fantastic because you don't want noise chattering up your inputs on your chip, creating problems. And then they mentioned the pull-up resistor mode, which in my mind is bound to this I/O buffer thing, the pin configuration controls. What do we got? Flexible on-chip clocking. All FPGAs have this sort of thing as well. Oh, by the way, all FPGAs usually, I've never seen an FPGA that does not have, selectable voltages and things for their I/O pins. Schmidt triggered inputs are not universal, but I suspect they're very common as well. Programmable pull-up resistors and pull-down resistors are very common on modern FPGAs as well. So the on-chip clocking refers to these PLLs. These are another thing that we'll probably talk about on its own. This refers to the ability of the chip to synthetically create one clock frequency given another one, which is really useful. So if you have like an oscillator running at 25 megahertz or maybe 50 megahertz, and you really need, say, 85 megahertz, you might have a way to configure this PLL to generate 85 out of the 25 or the 50 or whatever. So these are really useful. They're also very common on many modern FPGAs. The chip that we're going to use, the HX4K, has 2 PLLs on it. Although my particular project board only has an oscillator connected up to one of them, the other one you can use for whatever you want. Well, I talk about device configuration and flexibility and stuff like that. The configuration of an FPGA, they mix up, in my mind, their terminology a little bit. They refer to the SRAM inside the FPGA. Yes, there's static RAM in there, but that has nothing to do with this embedded block RAM, which also is static RAM, by the way. The device configuration refers to the fact that these LUT4s, that we'll talk a lot more in a minute about, they are just static RAMs, and what this stands for is look-up table. So what this refers to, a lot of what this refers to, are the values that you put in these lookup tables, okay? And they say it can be figured through an SPI interface. So you can plug this into a CPU or something that has an SPI interface on it, and you can just directly download right into the FPGA if you want to. Or what happens is the FPGA itself can become what's called an SPI bus master and talk to a flash chip, a regular old run-of-the-mill standard SPI flash chip, and then download a configuration out of that flash chip. And that's the mode that I'm going to use on my project board right here. This footprint right down here is for a flash chip. Now, I've also put this set of headers over here, and we'll talk about this in another video, but these headers, depending on how you put little jumper shunts on here, you can configure this so that a Raspberry Pi plugged into this connector over here can directly program the FPGA. You don't even need to solder in this flash chip if you don't want to, if you're going to use that mode, all right? Or what you can do is you can move the jumpers around and take your Raspberry Pi and directly program this flash chip here. So this SPI interface is the one we're going to use. You'll see scattered out through this datasheet reference to this NVCM, this non-volatile configuration memory. which is a one-time programmable ROM that's inside the FPGA, which is used if you're going to build a product or something like that, and you're going to make, 10,000 units, and you don't want to buy 10,000 flash ROMs. Well, once your program is all, designed and debugged, you can put it in this non-volatile configuration memory and ship your product out. But of course, this is one-time programmable, which makes it, in my opinion, utterly worthless for hobbyists. So we're not using this. All right? I don't even know how to do it. You need to have, I believe it's just hooked up to the SPI interface. There's some, commands and stuff you can send it to program this memory. And Lattice makes a special programmer for it that you can go get. But, if you're interested in it, you can go figure that out. Figure that one out for yourself. It has no point in my life because I don't build anything with enough volume to care about. I use the flash, or I directly program it from a host processor. Now, we get to one of the biggest reasons that I picked this particular chip for my project. It is available in a thin quad flat pack. That is, in my opinion, much easier for me to solder in by hand than any of these other packages. These are ball grids over here, the VQFP, QFN, and so on. These are the kind of packages that have little metal studs on the edges, but they don't have pins sticking out. You can solder those in, but to me, the quad flat packs are the easiest ones to use. So that is a big plus for me. There's another big plus that we'll see eventually in another video. When we program these things, there's a full-blown open source, freely available toolkit that runs on the command line with nice make files and stuff, good old style, the way I like to work. It's called Ice Storm. It's been around for several years. It's fairly well debugged. And where the HX4K chip is concerned in particular, it lets you do extra things that the Lattice software does not let you do, which is also a big plus. Well, we'll get there soon enough. In any event, this chip is in production. It's inexpensive. It's available in a quad flat. It has really simple programming software that is a standard package on a lot of Linux distributions as well, by the way. So there's a lot going for this particular chip. Therefore, I choose this for my simple designs. I don't need a fancy chip. Why require custom vendor software and all this other stuff when I can get this just bang right on the command line for free, okay? For free, relative term. A lot of the big vendors, all of them, Xilinx, Altera, and Lattice, do provide their software free of charge if you want to use the actual vendor software. If you want to try it, I wouldn't discourage it at all. Knock yourself out. But what happens is they all work differently. They're all constantly being updated in ways where the GUI changes and their libraries change. I mean, I've been using the Xilinx software for more than a decade, and every time they do anything, all their built-in code generators work differently. And I don't know, maybe they fixed that. Honestly, I haven't touched it in a couple of years, but wow. Upgrading has always been really difficult for me with the Xilinx software. It's great. It lets you do great things. Don't get me wrong. It's awesome. It's free. It's wonderful. If that's what you want to use it. The beauty of Verilog and VHDL, which are the languages that we use to program these things, is that they are incredibly portable. If you write code for this Lattice chip, it will work on the other ones. I mean, it's crazy how portable this stuff is. It's wonderful, okay? So I'm just saying, these are the reasons I chose this particular chip. You may have different goals and different opinions, but just so you understand mine, that's where I'm coming from here, okay? You can get them really super small, halogen-free, blah, 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 green for the earth, all that other fun stuff is available. That's all very common these days, almost all chips now. All new ones are that of that variety, simply because they have to in a lot of countries, right? So now we got this table down here. This gives you a comparison between the LP chips and the HX chips, okay? As you can see, the LP is up to 7680 and the HX also has up to 7680 of these so-called LUTs. When you buy an FPGA, it's really difficult to do apples-to-apples comparisons these days. It used to be you pretty much counted how many LUTs one had versus another, but now it's dependent on whether you have a LUT 4 or a LUT 3 or a LUT 6 or whatever. Those are different power levels you could think of in terms of the expressiveness of the kind of functions that you can do with one of these so-called LUTs. And again, we'll talk a little bit more about LUTs in a minute. But meanwhile, the more LUTs, the better. And a LUT 4 is better than a LUT 3, okay, and a LUT 6 is better than a LUT 4, and so on. But, then you have power issues. The bigger LUTs have more power consumption, and if you don't need them, then they're wasteful. So it turns into a real tuning problem if you really want to optimize your product or minimize your costs and ask yourself, what's the smallest one I can get away with, that kind of stuff. I'm not really going to get too much into that. Again, the main reason I chose this particular chip is because I can actually solder it in, and it's incredibly cheap, it's in production, it's well documented, and well supported. I'd use it even if it had LUT 3s, okay? So anyway, I'm looking at the HX4K, and what you got in here is you've got, a marketing person's upward rounding of the number of LUTs is what they use to determine the 4K, 8K, and so on. What do we got here? How many memory blocks does it have? It has 20, supposedly. It has 80K of these RAMs and so on. It has 2 PLLs, 95 maximum programmable I/O pins. Differential pairs, okay, and high current LEDs. Like I said, we don't have those on the HX. They've got them on the LPs over here, okay? But I don't need them, as I mentioned earlier. Now, there's a subtle thing about the 4K and the 8K that I didn't realize early on. It's very confusing. If you look at the configuration of the open source tools, half of the tools don't differentiate in any way between the 4K and the 8K. In fact, when you build a program for the 4K chip, what you do is you tell the compiler that you're targeting the 8K chip. And I thought it was weird, because what happens if you use more than this many LUTs? Is it going to fit in there, and so on? Turns out the answer is an overwhelming yes, because inside a 4K chip is actually an 8K silicon die. So I don't know if anybody knows the history of this. I'd love to hear about it. For some reason, Lattice differentiates between the 4K and the 8K. Lattice claims the 4K only has 3520 LUTs, when in fact it has 7680. It says that there's only 20 of these RAM blocks, but really there's 32, and so on. And I suspect there's one of two things happening here. Or one of three, maybe. Maybe they expected to have a separate piece of silicon for the 4K, and it turned out to be cost prohibitive or something. So they just put the 8K in the 4K package and said, there you go, it's 4K. Never mind the man behind the curtain. Okay, maybe that's what they did. Or maybe what they figured was, when they test the chips, when they manufacture them, maybe, and this is purely me inventing a conspiracy theory here, maybe these RAM blocks have a certain failure rate. And if some of them fail, but at least 20 of them work, they'll just declare it a 4K chip instead of an 8K and sell their mildly defective ones. I mean, vendors do this all the time, right? That's why they have the faster and slower CPUs. When they test them, if they don't run real fast, they just say this is a slower one, right? So maybe that's going on here. Or maybe there's a whole nother theory I haven't even thought of yet. I'd love to hear your comments below. If you really know the bottom line of this, I'd love to hear about it. Like I said, it really threw me for a twist. I was very confused when I configured the tools and the software to program the 4K chip. The beauty, though, is we're getting an 8K chip, even though it's a 4K chip. Now, if you look down here, these are all the different packages you can buy. Oh, if I want a 4K, I'm in this column versus the 8K in this column. And what do we got here? Look what happens. If I buy the 4K or the 8K and I put it in this, whatever this package is, it's a ball grid of some kind. Notice you have the same number of I/O and the same, what is the 13 over here? The parenthetical is this LVDS pins, right? So you're going to have 93 total I/O in this package and 13 LVDS. Look what happens over here. If you put it in this chip, you got 95 and 12. Now, you got this weird thing going on over here where they say, oh, we don't sell the 8K in the quad flat package, but we do sell the 4K. Okay, even though it's an 8K. Again, kind of weird. And then again, of course, they don't sell the 4K in these packages, but they do sell the 8Ks with the larger ball grid sizes, okay? So I'm not sure what this is all about. It may be, I doubt it, but it may be that if you look at the pinout for the 4K chip versus the 8K chip, they could actually have different pinouts on those ball grids. There might actually be a difference in some way. It turns out, though, it's not a difference in terms of the silicon inside. It may be a difference in the packaging, okay? I do know, for example, if you use a 4K versus a 1K, all right, and you look at the packaging over here, and I want to get a quad flat. See how it says 107 versus 96 I/O pins? The pinout of the 1K chip is completely different and incompatible in this package here, the quad flat. The 1K is very different and incompatible with the 4K. All right, so if you can't find a 4K and you want to build a board, don't substitute a 1K. It will not work. They are completely different. And again, I'd love to hear why, if anybody has an opinion on that. There's no doubt that they have different silicon, and maybe that has a lot to do with it. But still, it is a little bit of a nuisance when you're out of stock or something and you want to substitute. Do not substitute, okay? All right, so let's get to the good stuff. Here you go. Here's your big introductory architecture overview of this thing. Now, again, I choose this because it's a real simple FPGA, cheap, and so on. This is very typical, all right? So no matter what you buy, it'll be like this and probably more, all right? So relatively speaking, this is a very simple FPGA, all right? So look at this diagram here. I/O bank, what do you get? 0, I/O bank 1, I/O bank 2, I/O bank 3. A lot of FPGAs from Lattice and at least Xilinx, I haven't looked at a lot of the packaging from Altera in a very long time. I don't recall how they did it, but I believe they have banks just like this. I know Xilinx does. And a lot of what happens here when they refer to these banks, certainly with the Lattice and the Xilinx, they'll have a north, south, and a east and a west over here, okay? And some of the documentation refers to it that way, which I can be a little disorienting, as if you're looking from the top or the bottom or whatever. Sometimes that gets weird, and they sometimes refer to the thing on the left or the right. And I'm like, why don't you just give me pin numbers instead of that, please? So be wary of that, okay? Bottom line is you have multiple I/O banks, and usually, and in this case where the Lattice ones are concerned, each bank can run at a different voltage. The chip inside here, the internals of these FPGAs run at 1.8 volts, and that's a given. But these I/O banks can run at 3.3 or 2.8 or 1.8 or 2.5 or whatever. All right, so at the same time, you can have all these powered in different ways, to suit the needs of your application. Super flexible, super useful. Now, there's also certain rules, and I've seen this on Xilinx as well as this chip here, where they put a footnote in there and say the SPI bank has to run at 3.3 volts. And in this case, the SPI bank on the 4K chip, and probably the other ones too, I don't know about the other one, is in the same power bank as IO Bank 2. So sometimes there's these weird rules where you're going to have any power you want on bank 2 as long as it's 3.3 volts because it includes the SPI bank. Statements like that appear in these documents. So again, you got to read these things before you get too cute about, trying to be super flexible with them. All right? So that's the kind of things, the kind of restrictions that you'll see from time to time. These other ones are pretty much you can do what you want with in this particular case. Now let's look at this diagram. There's a PLL box here, and the 4K and the 8K has two of these. It turns out that there's a PLL on one bank, and the other PLL is all the way on the other side of the chip. So if you want to hook up one oscillator to both of them, it's kind of a pain in the butt because they're physically on the opposite sides of the chip. On the other hand, it's not entirely clear why you'd really want to do that. I suppose you could if you wanted to have many different clock frequencies all coming from the same oscillator. Having them on opposite sides is convenient if you have two separate actual oscillators, physical oscillators. Keeping them separate like that can be useful. So different vendors are going to do different things with their PLLs and different numbers of them and hook them up in different ways. That's just the way the 4K quad flat packaging does it. So what do we got here? We got all these PLBs. We already talked about these RAM blocks, of which there's 32 in the 4K, 8K mystery combo chips, as we saw on the table above. And they're scattered around inside the FPGA amidst all these so-called programmable logic blocks. And you can see in here it says programmable interconnect around the outside. Okay, it turns out the programmable interconnect is a big X and Y crossbar hash of wires, almost with a hierarchical subset of wires. In other words, I can hook one PLB up to its neighbor really easily, but if I want to hook this PLB up here to the one way over there, there's more limited resources to go a long distance on the chip than there are local resources, okay? Now, when you get to configuring and programming these things, fortunately the software figures all this out for you on its own. However, when you have a really high-performance design, or you're trying to use the entire chip and you have no spare resources, the software doesn't always work. It can't figure out how to get it all in there necessarily. So some vendor packages, and this is where you start, saying, well, the open source stuff can only go so far. The vendor stuff has increasingly sophisticated ways of letting you help it figure out where everything should go. So-called floor planning logic, all right? Where you can say, I know that I want, a bunch of data latches stored in this PLB, and I want this 4K RAM here to be used for some purpose because I know I have a lot of traffic that connects these things together, and I want them nearby so they can go really fast, that kind of thing. And then you might say, I know that this PLB over here is only connected for one purpose, and I don't care if it's a little bit late. So it can be way far away from this other data processing area that you might want to put here on the FPGA. Now, this is super advanced stuff that only comes into play, you're really at the limits of the performance of the FPGA, and you really have to get everything just perfect. And or when you put so much in the FPGA that while it can fit, it might only be able to fit in certain ways that the automatic software can't quite figure out. I'm not going to get there in this series for a very long time, if at all. All right, so don't get too worried about these things. I just want you to let you know that these things happen. You might read about it, you might hear about it. This is more advanced stuff than you need to deal with if you just want to hook up a bunch of, fancy I/O type controllers and program them into the FPGA. That sort of thing usually works pretty easy, fully automatic, no brainer. It's just going to go. But it's nice to know you have this wide variety of control capabilities of the various vendor software packages. And it may also be one of the reasons you pick one vendor versus another one, because their software allows you to do things, oh, I want to do floor planning, I want to do this certain kind of thing. And maybe other vendors don't do that, okay? So this is where they, really get into differentiating themselves, or they can. I haven't looked at the big boys lately. They tend to copy each other. So if you get something cool in one, it's usually available within a few years on the other ones as well, all right? Okay. So what's this PLB? What happened to these LUTs and all this other fun stuff? Well, a PLB is exploded out over here. If you look at these little footnotes down here, look, this is your 4-input lookup table, all right? That's what the 4 stands for. What happens is there's 4 binary bits here that go into a lookup table, and a lookup table is just a static RAM. It's a 1-bit static RAM that has 16 1-bit addressable values in it. You have 4 bits over here that go into the LUT. That's your address. You have 4 bits. You can go from 0 through F in hex. That's 16 in decimal. Different combinations. Depending on the 4-bit value that comes in here, it looks up what's in that memory, and that 1 bit comes out on the right side over here. That's what a LUT is. It is a lookup table, nothing more. It literally is what the name says, which is a nice rarity these days in technology, okay? The name is so meaningful, it sounds like you must be wrong. That's how simple these really are, okay? So if you think about it, what you've got here now in a LUT is a truth table. That's literally what these are. You just download a bunch of ones and zeros into this 16-bit RAM, and you say, when I have 0000 in here, take the first bit in address number 0 in this lookup table, and whatever's in there, make it come out. Okay, so if I want a 4-bit AND gate, a 4-in AND gate, that's obviously 16 different possible values. And we all know the AND function is true on its output when all of the inputs are true. So what you would put in this lookup table are all zeros, and in the very last row number 16, when all the bits are high, you'd put a 1 in there. That is an AND function with 4 inputs, plain and simple. That's what makes an FPGA an FPGA, and not a CPLD or a GAL, PAL, PLD, whatever other names those other ones have that came before the FPGA. These use lookup tables, all right? The other ones use a circuit, which is called a sum of products usually, and they have tons of gates in here that can literally calculate any one of those values. And what you do is when you program them, you basically disconnect the gates you don't want involved in the function. So what happens is those chips, while at the time were easier to manufacture, don't scale so well. By the time you have thousands of these lookup tables, you would end up having so many gates in there and so much interconnectivity between all those gates, and the programming requirements would be horrific, of course. And remember, the way those things work is you literally shut off what you don't want. So you end up having an enormous amount of stuff in there that's shut off, that's wasting power when the chip is in use. They're just disconnected. They're not, powered down. Suppose, in modern technology, somebody could figure out how to make all that happen, but that's not how those work, okay? So there's power problems, there's programming problems, there's just scaling problems up the yin-yang with those older designs. So when they use lookup tables like this, we have a whole new world we're living in, okay? Now, you can accomplish a lot of the same things with the 2 different chips. The CPLDs have a lot of functionality in there, relatively speaking, for that era, okay? But there's nowhere near the kind of number of logic cells that you're going to get in a larger FPGA today. No, even the biggest CPLD won't even come close. biggest CPLDs will be similar to these HX chips at best, okay? So these are these HX chips from Lattice are relatively simple in the realm of FPGAs because they don't have a lot of these special functions in here. It's almost entirely just PLBs and one or two PLLs and some RAMs, right? All FPGAs have stuff like that, and all FPGAs have a way to program them, okay? The other ones that are fancier have things like Ethernet controllers in here. They might have hardware SPI controllers, I2C. They might even have a whole CPU inside here. Like the Xilinx Zinc series chips have ARM processor cores inside here. Well, yeah, you could create an ARM processor core by designing one and implementing it using a whole bunch of LUTs, but that would take more power than if there was an actual one sitting right inside the FPGA. And because it's not that uncommon to want to combine an FPGA with a CPU, that vendors provide such things. Xilinx, I know, supplies a Spark core inside an FPGA. It supplies ARM cores in their Zincs, and there's probably others. I would expect to see RISC-V showing up by now, around now, if they aren't already available. And again, it's useful because you get more performance, less power consumption if you have custom specific, what they call hard IP inside the chip, okay? IP in that context refers to intellectual property, and you see that bandying around a lot with FPGAs. Vendors say, oh, we have an IP library. And what they're really talking about there is they have a whole bunch of things like if you don't want to design your own UART, you can just go over to Lattice and say, I want you to give me the UART code so I can put one in my FPGA or an I2C or an SPI or whatever. And usually all the simple ones are available. Then they have some fancier ones to deal with if you have a large, memory chip or something that you want to hook up to your FPGA and you don't feel like figuring out how to implement the SDRAM state machine or something like that. You can just download one. Most of the bigger FPGAs, the modern ones, usually also have full-blown hardware, hardwired, DRAM controllers built into them as well. So again, that's when you differentiate between the different chips, and we're staying simple here, okay? Jumping around a little bit, but I want to make sure everybody has their a good sense of where we are in the world of all the terminology as you look around at all the different chips, okay? So I talked a little bit about what the LUT does. I mean, that's really all there is. There's nothing more to it than it's a lookup table. There's this thingy over here. What's that all about? It says carry logic. Well, it turns out that adding and subtracting values are really common things to need to do. And if you think about grade school, right, if we turn this on its side, let's see if I can do that. R, one of these menus here. There we go. You turn this on its side. Of course, it's backwards. Let me turn it around another 180 degrees here, and then it'll match what I want to say. It's sort of upside down. The output's on top, the input's on the bottom, but you kind of work with me here. Notice this goes from the right over to the left. And what they're referring to in this here is that if I want to add a bunch of numbers together, in this case, two binary numbers together, 1011111 plus 111000 or something like that, I'm going to put the inputs on some of these pins down here. We may not use all of them, right? We'll certainly use two of them. We'll hold the inputs of the two values we want to add together for each column, okay? Again, back to the grade school. What did you do? You added the right column digits first because you needed to figure out if there was a carry. If there is, you would put a third number in this next column. There'd be the two digits you want to add together plus another digit on top representing the carry. That carry needs to be known before you can complete the addition in this column. The carry being the one from the first column. So the second column here, what we call a full adder circuit, has the two inputs that you want to add plus a third input which is the carry from the previous column. So what do you suppose happens once you're way over here? This is only 8 bits. What happens if I want to add two 32-bit numbers together or two 64-bit numbers together? Well, the guys over here are dependent on what comes out of here. And this one, what comes out of here, is dependent on what comes out of here, which is dependent on this, depend. So what happens is the time at which this thing can spit out its sum for this column requires this one to finish its addition, calculate its carry, this one to finish its one, calculate the carry, finish, calculate, There's a lot of gates involved in this, okay? Now, this is what we call look-ahead carry logic. And that's how you optimize these things. If you want to be able to add faster than just simply waiting and waiting and waiting, as you add more bits to the width of your registers, right? God forbid you want to add a pair of 128-bit values together. It might take an hour. There are ways to calculate the carry and the output at the same time so that so that it gets available sooner than it otherwise does, okay? You can read all about that. I'm sure there's Wikipedia pages on what we call look-ahead carry, okay? That's what's in here. They provide these on a per PLB basis. So a PLB is just a bunch of lookup tables and some output circuitry. They'll give you a zoom in on that on the next page. And it also has these look-aheads, all right? So this is the first clue here about what I was talking about earlier, what we call, planning and the floor planning. If I want to put two binary values together and I want to add them, it's kind of important that you put the input bits into these LUTs in a pattern so you can take advantage of this look-ahead carry logic. Now, the automatic, the programming software does all this automatically. We're not even going to think about this possibly for a very long time, if at all. But you need to understand it's there. The reason you need to understand it's there is because this impacts the speed and the performance of what you're doing. When you run the compiler, it'll give you these various reports, and it'll say things like, the longest look-ahead carry chain has so many bits in it, and the amount of time it takes to calculate that carry is so many picoseconds and stuff like that. It'll show up in these timing analysis outputs that we'll see when we compile our code. And if you have problems because your program doesn't work fast enough, those bits and pieces of information are what you're going to have to figure out how to improve upon, okay? So do you need to know this to program it? No. Do you need to know this to fix a broken program? Well, it depends on what's broken and how fast you want it to go, okay? So this is all good stuff to know, but fortunately, you can ignore it unless you're trying to do a lot with this FPGA at a very high rate of speed, okay? And everything speeds up, everything starts getting important, all these little subtle things, okay? So I just wanted to make sure that we all understood what's actually in here, how these interconnects work, what the look-ahead carry chain is. All FPGAs have a look-ahead carry chain. All FPGAs have this big programmable interconnect. All FPGAs have more connectivity between nearby LUTs and PLBs than they do between a PLB and something far away. I mean, this just makes sense, right? Because there's only so much silicon in here, and the density of all those wires gets to be problematic. So, again, duh, once we think about it, okay? You just got to be practical about these things. So here's a zoom in on what's going on with these, each one of these logic cells inside the PLB we were just looking at. So there's your LUT, okay? Here's the carry logic, and you can see there's muxes in here, and this bit's high. I haven't traced through how the carry logic really works. I'm not that concerned about it and never really pay a lot of attention to it myself, except for when I'm adding large binary numbers together, because it does take time and it does interfere with the speed that your application will run. This over here is more variable on a per FPGA and per vendor basis. The short of it is, you've got what is basically a logic gate here with 4 inputs and any kind of a truth table you could possibly conceive of that you can put in here. And there's your output. Now, in the ICE40 family of FPGAs, the LPs and the HXs, they have a flip-flop over here, a D latch. And the latch has, you could, if I want to, if you think about this, I can take the data coming out of this gate and I can send it right out of the logic cell. So whenever this thing changes, the output changes right away. And don't even use this, ignore it. Or I can use this gate and maybe the inputs are not always stable, but once in a while I have a value that it's calculating that I want to latch into and remember. Well, I can clock this flip-flop, and you can see this goes up here to the thing called clock, and this will remember and latch the value at the time I said, hey, save this one, okay? Then the inputs can change, but the value in this flip-flop stays constant, and I can tell this mux, use this output here as the output for the logic cell versus, or instead of, just propagating through the one from this gate. All right? So you've got a combinational circuit here, if you use this route, or a sequential one, if you put a latch in there, and latch it and hold it until the next time you hit this clock over here. All right? Now, notice it says shared block level controls. Clock, enable, set, and reset to control this flip-flop. You only have one set of signals for the entire PLB. All right, so all 8 of these have the same clock, enable, and reset. And you can also you can set these to just never reset it or never enable it. Well, actually, it's either always enabled or occasionally enabled, right? And the clock, the way this is drawn here, can either be a rising edge or a falling edge, depending on how you configure this, okay? But these 3 signals are the same for the whole PLB. This limits your abilities, okay? You have a lot of stuff in here, and you got a lot of PLBs, but each one of those PLBs, the 8 LUTs in there, all have to use the same signals for these things on these latches. And this is not a big deal at all, because whenever you're doing this sort of thing, you usually, well, you're not always doing it this way, but quite common, you're going to have an 8-bit latch or something like that in your design, and you want all 8 of them to work together anyhow, so this is fine. Even if you don't have an 8-bit latch in your design, it's incredibly common, as we will see, to have one clock run your entire application and your whole FPGA, as well as the reset signal. These are called global clocks and global resets when they're used that way. And they have special provisions for that because it's so incredibly common that when we look at the pinouts and stuff, you'll see there'll be things called global clocks and global reset. And that's because what happens is these interconnects, some of the lines that run around the entire FPGA, those are what we call the global lines. There's 8 of them in this particular design. There's 8 global clocks. Is that true? Is there 8 and 8? Or actually, there's 8 global lines. That's what it is. And 4 of them can be used as global clocks, and 4 of them can be used as global resets. So it turns out when you design your circuit, if you're going to have reset and clock signals coming into an I/O bank somewhere, it's important that you pick the specific pin that is connected up to one of these global networks inside here, because it can run more efficiently when you do that. In fact, most of the software that I've used will give you a warning if you try to use, pin 105 as a reset, and it's not a global reset capable pin. It'll say, suggest you use pin 90 for that. Your circuit will work better, okay? You don't have to, but it does work better if you use the right pins. I point that out because there's some foreshadowing in here. I may not have hooked up my little test board here on this website that we saw earlier. Some of these pins are not always perfectly optimal, right? I tried to hook the clock up to a global network, but you also need to have it hooked up to a PLL if you want to use the PLL, and which pins you use limit the functionality of neighboring pins and stuff like that. So we'll have a closer look at that, why I did what I did, and what we can all debate on what's better, what's worse. This is all the give and take, pros and cons, and all the kind of decisions you have to make if you want to design an FPGA into a product. Turns out most of the decisions are pretty straightforward. You just need to know which choices you need to make so that you're not completely oblivious to, oh, gee, I should have hooked the clock up to a clock input or something like that, all right? Just to understand they do exist, and this is why, because they're shared. And some of them are shareable across every PLB all at once. All right, so if we come down here a little bit, we see these tables. You're going to read this manual. What'll happen is each time they talk about something like a logic cell, all right, there's going to be a logic cell, then we'll talk about a pin on the physical chip. They'll have these tables that say these are the controllable items for whatever that thing is. In this case, it's one of these logic cells. So it formally defines each logic cell has 4 inputs. It has an enable, a reset, a clock, an FC in for the fast carry. It has an output data pin and a fast carry output. As if it's not used, then the flip-flop is never going to be set or reset except for when cleared immediately after configuration. Okay, well, flip through this manual. I'll talk what does it do when it's being configured, and how does it transition from being configured into running, okay? So you'll see these footnotes all over the manual. During configuration, this is going on. After configuration, it does some other stuff, okay? Again, just to get your bearings here. These tables are super useful because you have the option as the user of this FPGA to either program the FPGA by creating a bunch of these items, in this case a logic cell, and telling the FPGA what to do with these pins, or you can use what we call behavioral programming, a really higher level view where you ignore all these cells, and that's normally how everybody does it, except for incredibly sensitive situations or very customized situations where Verilog can't automatically or VHDL or the HDL language in general that you're using, can't figure out how to map the functions you want into what it has to work with. But the HDL languages that we use know a lot about logic cells. They know how to do this. They know how, if I say I created a variable A and a variable called B, or in this case, wires or registers or whatever you're going to use in your design. We'll talk more about that later. But effectively, 2 variables. Do you want to say, C equals A plus B? It knows how to create a carry chain, and it knows that they all need to be in groups in the same PLB, and it'll just make it so. Okay? So you don't have to worry about all this stuff, which is great. Okay? Otherwise, this would be incredibly tedious. I can't imagine what happened before they started using these HDL languages. It must have been a lot of work to configure these various blocks. In any event, you're going to see these tables throughout the manual. These are the things that you're really working with, is my point. You're going to hear about them and see about them in the compiler when it says, here's how many logic cells are used, here's how long your carry chain is, here's how this works, and that. They're going to refer to these things, especially when there's a problem, like you run out of resources or it doesn't go fast enough. These are the words that you're going to see spewing out of the compiler. Now they talk a little bit about the routing and the control and the distribution network and these global buffers and the global clocks and so on. And here's this table, which I should have looked at earlier, with the 8 global, these are these global routing buffers, they call them, but they're connected to pins. If you can connect them to pins, I should say, if you want to, and it's very nice when you do, because if you don't hook your oscillator input to one of these, and you can't conveniently run it as a clock to all those D latches if you want. And if you have a special reset signal that's not on a even numbered G-buff pin, okay, then it's not going to conveniently be able to be connected to all the resets on all the D latches at once. It'll have to use a lot more resources, and some of them will reset quicker than others. You could have timing issues with your design. That's the point, okay? The clock enable on the various D latches are hooked to the odd-numbered G-buff pins. If your design requires a really efficient external source to generate these signals, you want to hook it to the right pins. Otherwise, it won't go so fast, okay? That's why they give you these tables. Global high Z control, global reset control. You'll see a bunch of stuff in here about what happens when the chip is being reset. Is that what I'm looking at? A section of this is routing, I guess. But what happens is the high impedance controls, it'll say during the configuration process, all the things are put into high impedance. And during the configuration, all of the flip-flops will be reset. And then when the chip wakes up, what does it do? It'll say all the flip-flops will be in their defined wake-up, what does it say? Global reset signal is automatically exerted throughout the configuration process, forcing all the flip-flops to be defined in their wake-up state, whatever that is. For the PLB flip-flops, the wake-up state is always reset regardless of what the primitive says in the application, which is interesting because if you say, I want the reset state to be a 1 versus a 0, this is saying that won't happen. I wonder if this is poorly worded, or we should probably test this at some point. I personally don't count on the chip waking up in a specific state. I design a reset signal into my application, and we'll see how that works when we start writing applications. And I use that to reset all my flip-flops, mostly because you want to be able to reset your application, if you want to be able to reset your application without rebooting the entire FPGA, you still need to have a global reset of some kind anyway. And I say global reset, but this one's referring to the one and only real global reset that's a hardware thing inside the FPGA when it boots. Let's just use the word boot for this. That's what they're talking about, the boot up reset. I'm talking about these resets, which are the reset controls on the flip-flops that you can use to reset the flip-flops without rebooting the entire FPGA, okay? So I believe that's what they're talking about in here. Give it a closer read if you are concerned about that sort of thing. Bottom line is, I always expect the FPGA to boot with random values in its latches, and then I assert a signal in my application design that sets all my registers and latches and stuff to a known state, and I operate from there, okay? Now they're going to talk about PLLs, as I said before. We'll talk about these in a separate time, but the short of it is you read the rules, and they even have a little tool. You just type in, I want this frequency. I've got a reference clock from an oscillator, like in my board design, I think I put a 25 megahertz oscillator in there, and maybe I want a 40 megahertz signal, and it says, well, in order to do that, set this to this value and that to that value and so on, and configure this like so. And it'll say then the output value will be, whatever frequency. These are not perfect. I mean, they can't generate any frequency at all from any other ones. I mean, there are a lot that it can do, but if you want a weird one, what it'll do is, like, let's say it cannot generate 40. Let's say I want 40 megahertz, and I got 25. And let's assume, for whatever reason, it can't give me the actual exact frequency I want. It'll say, well, I can give you 39.99999521183, which might be good enough for my purposes. And if you want that one, then do so. All right? So it can come close when it can't do the right thing. And of course, you're limited to, like a couple hundred megahertz or something like that. It's a pretty simple FPGA, and it can easily do 100, 150, or even, I think, 200 megahertz on a lot of parts inside of it. So if you're pushing it, you can get high frequencies out of these things. But as you move into those high frequencies, your carry chains become very important, and you'll learn a lot more about that if you're going to try it, okay? We'll talk more about this some other time. I'll show you how to use the tool to just calculate the values so you don't have to do it all by hand and guess your way through this. And here's another one of these tables. So this table, you'll see, will match the values we have to provide the configuration tool that we're going to use, or more accurately, these come out of the configuration tool. We say, I want a 40 from a 35 or a 25 megahertz. And it'll say, well, use these values for all these variables here when you configure this PLL. And there's a way to do that in Verilog that says, this is not a Verilog thing. This is like a high-level vendor-provided macro. And I need these values to magically go into that PLL, please. Thank you very much. And you just type them in. And this is incredibly common. All the vendors do this. For all of this is what we call these hard IP. Okay, the Verilog doesn't know how to configure a PLL, so you have to do it for them and say, create this module. It looks like Verilog, or VHDL has the same thing. And you instantiate it, they say. In a higher level programming language like C, it would be like calling a subroutine. It's the HDL equivalent of calling a subroutine is to say, create a circuit. And it looks in the source code like you're calling a subroutine. But you're not. What you're doing is creating hardware. So here's how you create the configuration for a PLL. All right? And the same thing happens with block memories. We'll talk about these when we use them. This down here tells you that you can configure the block RAM to operate as if it has 16 bits per addressable unit, 8 bits, 4 bits, or 2 bits. Obviously, if you're using 8-bit values, you can have twice as many as if you have 16-bit values. Because no matter what, you've got a 4K bits. And how do you want to arrange them? Do you want to exchange 16-bit values, 8-bit, 4-bit, whatever? So what you do is you use these configuration primitives, not unlike how I described the PLL. You can say, I want a block RAM, one of these sysmem blocks, or an EBR, or whatever word they decide to use to refer to this thing on whatever paragraph we're in right now. And you say, I want a 512 by 8 NW or an NRW, blah, 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 whatever way I want it configured. Okay? We'll configure up a few of these and make some FIFOs or some RAM blocks or something in a project down the road. But this is the high-level view just to understand what we got to work with when we use these RAMs. And they should give you, here's a nice picture. Schematically, it would look like this. It's a dual-port RAM. I can write and read at the same time with different addresses because the write address and the read address are totally separate, independent things. And these are the specific variables you need to configure when you create one and what they all mean. All right. Here's your sysio. These are here we go. Here's the pins, all right, these PIOs. So we were looking at these PLBs. We looked at the block RAMs. The PLL is not in this particular picture. We're ignoring. Remember, that was the NVCM. The SPI we'll talk about when we actually try to configure one of these. We'll talk about this when we look at the schematic of a breakout board. And in these I/O banks are these things, okay? So we didn't see one of these before, but that's what's in these general purpose I/O banks. We have a different voltage for each one if we want. I'm going to run all mine the same, keep it simple. I'm going to go 3.3. These chips don't run at 5. There are certainly no modern FPGAs that run at 5 volts. And I know of, you're stuck in the low volt realm if you want to use these modern chips. You're going to have to do modern things. So what does it show? You got to pull up in here with an enable on there. It's something that I can set if I want to. The pad is where the physical wire is connected to a physical pin. That's what they're referring to here. You'll notice there's some circuitry that outputs to the pad and other circuitry that inputs from the pad. So therefore, what we're looking at is each pin can either be an output or an input, or even both at the same time. Okay, because you can see we have high Z control. This is a tri-state buffer, which means you can drive it to a 1 or a 0, or it can let the pin float. How else can you have an input, right? You have to be able to disconnect this thing, go into the high Z state in order to do that. You can have the input running. You can see there's a direct path through here without any special stuff going on. If you want, you can use this as a latch, just like you can have these latches on the output of all these logic blocks and these PLBs. You can do the same thing on an input pin. You've got noise chattering over here, and you only want to look at it once in a while. Latch the value when you care, and ignore it the rest of the time. You can route the signal through here. You just want to know what it is all the time, always. You route it straight through. There's a special feature called an ICE gate. This is a vendor-specific thing that allows you to kind of get a hybrid of the two things. I have never used it, but it has to do with when the value is changing and you want to see it changing without using a latch, you can route it through here, but you can also shut it off so that if it's chattering when I don't want to see it chattering, I can latch it and stop it. Okay? That's what this thing is. Now you might say, why don't you just move it back and forth between these two things? Well, it turns out that how you configure this mux over here is static. Once it's configured, you got to use it. You can't change. You're either using the ICE gate, the pass through, or a latched input. Okay, so this is some sort of a hybrid circuit. You can dabble with it later. If you have your favorite uses for this thing, let me know in the comments below. I've never actually used it in my designs. I either go direct or I latch it. What happens over here? Here's the output signal. As you can see, there's a path that allows me to go directly out. Okay, in our early designs, that's probably what we'll do. On the other hand, it might be that you've got a circuit that's combinational, but you want to change it to sequential, and maybe it's chattering along, and you say, this is the value I want to come on out that pin, and hold it steady while I do other things in my circuitry that I don't want to be changing out here. I can latch it. So I can route the signal through here if I want to. And if I want to latch it and then output the opposite, I can invert it on the way out of the pad. I mean, there's a lot of these optional features when you configure these how you want it to work, okay? Up here is the control that allows you to decide if and when this output signal should even be present on the pad, because this, as you can see, controls the high impedance control on this buffer here. You can say it's always to be connected to the output pin, in which case, you know, if you're going to read anything from the input, you'll be reading your own output. In other words, this is not really something useful in that case. Or you can have it permanently disabled and never output anything on this pad, but you're only inputting. That happens too, right? Or you can sometimes output and sometimes not output and do it dynamically only when I say, and then you can clock that one just like this. They give you lots of options, okay? So we'll talk about this when we configure various pins to do the things that we want it to do, especially if we're going to do something like an I2C interface where you need a pull up, and sometimes you've got an output and other times you've got an input, and you're switching these things around. So that will be really useful to know, or to be aware of all these options when you're building a circuit like that. When you're just lighting up an LED or something like that, you're just running an output through here. This is off. It's permanently on up here, and you just let her fly. Okay? Simple stuff, simple. Hard stuff, not so simple. By definition, that's what makes it hard, right? All right, so that's mainly the whole thing that I really wanted to talk about today. Here's the, they're going to talk about more complicated things. When you run these in pairs, This is more useful for DDR and LVDS. I think this is in reference to LVDS right here, actually, because they have differential outputs, or one of them's high and the other one's low at the same time, and they flip back and forth. I'm not going to play with LVDS, so I don't really care so much. And they'll probably talk a little bit about down here. What are we in here? Is this now the I/O buffer, the timing, and what it does at the different voltages? And I mean, this is all pretty specific stuff that's beyond the scope of what I really want to deal with here. And you can see back to the volatile stuff, and we get into programming and all that, which we'll talk about when we actually program one of these things. And as I said before, you got all your voltage settings and how fast does it go and how sensitive is it to various things, okay? How do you turn the power on? You know, if you have very fancy setup and each bank is running at a different voltage, there is an order in which you want to power these things up so that you don't damage something internally. If they're all set to the same voltage, you physically connect all the pins together and you just slam all of them on all at the same time to 3.3 volts in my case, as well as the 1.8, and it works just fine. I copied my design from the Lattice's own evaluation board recommended designs. So I can see this is getting a little bit long at this point, and I have covered what I wanted to cover here. I would encourage you to look at the rest of this manual just to understand what's in here. If a question should come up, you at least know what's in here so you can refer back to it. You're going to repeatedly see things where the 4K and the 8K chip have suspiciously identical ratings all the time, all the way down to things like when you configure a 4K chip, the memory that you download into the chip has the exact same number of bits as an 8K chip, which seems odd. Why would there be the same amount? Where when you configure a 1K chip, the amount of data you download into the FPGA is significantly less. All right? So all the power ratings, the memory configuration, and all that stuff of the 4 and the 8s are identical, and the 1Ks are always different. So again, it supports the fact that something weird's going on between these 4K and these are the LPs. The HX 4K and the HX 8Ks always have these identical values, which is, I consider quite suspicious. 15.7 and so on. Every time. Ding, 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 8.2, and yet this one's different. So, I don't know. It's a marketing thing, maybe. I don't know. Why do they differentiate between the 4K and the 8K? I suspect that what happened was they had different plans that didn't work out, and they just made them all 8Ks. There had to be a cost savings to just say, forget it, make them all the same. And, of course, if you get into LVDS, how are you supposed to hook it up, and how do you use the resistors or termination and all that to make it work right? Okay? So, again, give this an eyeball. We'll come back. Next time we'll talk about how to actually take this and put it onto a circuit board by walking through what I did with this particular design, and I'll tell you my rationale between various design choices, and I'll point out some of the limitations that I'm aware of. Feel free to chime in and let me know of any other limitations that I unknowingly may have designed into this setup, and maybe we can compare it to some other eval boards you can go out and buy if you don't want to build one. All right, so thanks for watching. I'll see you next time.